Welcome to The Explainer. Today, we are cracking the code behind one of the most famous icons in all of science, the periodic table. And you know, it's so much more than just a chart you memorize in school. It's really a map of the universe's building blocks, a guide to how they act, and an amazing piece of scientific detective work.
So, I want you to imagine something. Picture yourself back in the mid-1800s. Scientists have discovered dozens of unique chemical elements, and each one has its own distinct personality. I mean, some are super fiery and reactive, others are just calm, totally aloof. How would you even start to find any kind of order in all of that chaos?
Okay, so let's dive right into this detective story. We're going to follow a century of clues, a few false starts, and some real moments of genius that led to this incredible map of matter itself. Our story really kicks off in the 19th century. You see, chemists were convinced there was a hidden pattern to all the elements. They had to find the right key to unlock it.
The first big clue came way back in 1815 from a guy named Johann Dohrao. He noticed that some elements seemed to show up in threes, or what he called triads. So take lithium and potassium. If you average out their atomic weights, you get a number that's almost exactly the atomic weight of sodium, which sits right between them in how it behaves. A hidden relationship was definitely starting to emerge.
But here's the catch. It was only a partial key. This really elegant triad rule, well, it just didn't work for most of the other known elements. So the search for that bigger, universal pattern had to go on.
Okay, let's fast forward to 1864. The next big attempt came with a pretty creative musical twist. A chemist named John Newland arranged the elements by weight and found that their properties seemed to repeat every eighth element, kind of like the octaves on a piano.
It was a clever idea, for sure, and it actually worked pretty well for the lighter elements. But as you can see, once you moved past those, the music stopped. The pattern just completely fell apart for the heavier elements. So, nope, this was not the universal key they were looking for.
And this brings us to the hero of our story, Dmitri Mendeleeff. In 1869, he didn't just find another little clue. He had a breakthrough that was going to change chemistry forever.
Mendeleeff's big idea was actually simple but incredibly powerful. If you line up the elements by their atomic weight, their properties don't just change randomly, no, they repeat in a predictable periodic pattern.
So based on this law, he created his famous table. He arranged all the elements into horizontal rows, or periods, and he made absolutely sure that elements with similar chemical behaviors fell into the same vertical columns, which he called groups.
And this right here is where it gets truly brilliant. Mendeleeff was so confident in his pattern that when an element didn't seem to fit, he didn't assume his theory was wrong. Instead, he just left a blank space. He actually predicted that a new element existed there just waiting to be discovered. And you know what? He was right.
But Mendeleeff's key, atomic weight, it wasn't quite perfect. There were a few small but really nagging flaws in his table that pointed to a deeper mystery.
The problem was something scientists started calling anomalous pairs. See, to make sure elements with similar properties stayed in the same chemical family, Mendeleeff occasionally had to break his own rule. For instance, he put the heavier cobalt before the lighter nickel just to make the pattern work. But why?
This created a huge puzzle. I mean, if the whole organizing principle was atomic weight, why were there exceptions? Was the entire periodic theory flawed, or was atomic weight just not the right key after all?
The final piece of the puzzle, the true master key, well, it wouldn't arrive for another 40 years. But when it did, it would resolve every single one of those lingering contradictions.
So in 1912, a physicist named Henry Moseley was studying elements, and he discovered a property that was even more fundamental than their weight, one that would finally perfect the table. He found the atomic number, and it's really simple. It's just the number of protons in an atom's nucleus. Now, unlike atomic weight, it's a clean, whole number that is unique to every single element. Hydrogen is 1, helium is 2, and so on. This, he realized, was the true organizing principle. And this insight just cleared everything up. Atomic weight, you see, can have these slight variations because of things called isotopes, but the atomic number is absolute. When the table was reordered by this new, more accurate key, all the problems, like those pesky anomalous pairs, they just vanished. The puzzle was solved.
So, with the code finally cracked, let's take a quick tour of the modern table that we all use today and see how it works as our map to the elements.
And here it is,
the finished product of over a century of deduction and discovery. A perfect, logical arrangement of all 118 known elements organized by their unique atomic number.
So each little box on this table gives you an element's core identity. You got the name and the 1 or 2 letter symbol. You also see the atomic mass, that's the decimal number we talked about before. But the single most important piece of info is that whole number at the top, the atomic number. That's its unique address on the chart.
The table's structure itself tells a story. As you read across a horizontal row, or a period, you see properties change in this gradual, predictable way. But when you move down a vertical column, or a group, you find elements that act like a chemical family, sharing really similar behaviors. And that's what makes this table so incredibly powerful.
This family idea is so useful. For example, just look at Group 1 over on the far left, the alkali metals. They are all so reactive, they'll literally burst into flame in water. Now, compare that to Group 18 on the far right, the noble gases. They are famously stable and unreactive. Their position on the table is basically a cheat sheet to their personality.
You know, going from a chaotic jumble of elements to this elegant, predictive map, the periodic table is just a monument to our scientific quest for order. It's a puzzle that took a century to solve, but it's one that always leaves room for the next discovery. So, you have to wonder, what are we going to add to this map next?